Sometimes we will encounter quadratic equations that we can't solve by factoring. Some polynomials just can't be factored easily. And when that happens, we can turn to the quadratic formula. The quadratic formula has the advantage that it gives us the solution to any quadratic equation we happen to run into. The downside is that it's occasionally complicated to apply and use. So it's not something we're going to use every time, but it's a good thing to have in our back pocket for when we need it. So the quadratic formula reads as follows. The solutions to the quadratic equation ax squared plus bx plus c equals 0 are the following numbers. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So this is a formula that we use a lot. You may want to spend some time memorizing it because it comes up very often and it's very, very useful. It's potentially the most famous formula in all of algebra, possibly all of mathematics. And it gives us the solutions, as the statement says, to any equation in the form ax squared plus bx plus c equals 0, which is exactly what quadratic equations are. Now, it's important when we apply the formula that you keep track of what a, b, and c are. A in this formula is always the coefficient of x squared, even if the equation is written a little bit differently. B is the coefficient of x, c is the constant. So your best practice when applying the quadratic formula is to always put the equation in the form ax squared plus bx plus c equals 0 before applying the quadratic formula. Let's see an example of how we use this. Let's say we want to find the solutions to the equation x squared minus 2x minus 1 equals 0. Now, if you look at this for a little bit, you'll realize that we actually can't factor this. There are no integers anyway, whose product is negative 1 and whose sum is negative 2. And so we're not going to be able to factor this in the way that we did the problems in the previous section, and we're going to need something else. Well, here's where the quadratic formula can help us. Now, we don't always need to do this, but especially when first encountering the quadratic formula, I find it very helpful to be very explicit about what a, b, and c are in these problems. Now, a is the coefficient of the x squared. This problem doesn't have a coefficient of x squared written, and so that means that there's an invisible coefficient of 1 sitting there, which we have to include. B is the coefficient of x. It's the number being multiplied by x. And it's very important, absolutely vital, that you include the negatives when they appear. X squared minus 2x minus 1 is what we've got. And so that negative goes along with the 2. Remember, negatives always attached to the numbers to their right. And so our b value here, the coefficient of x, is negative 2. Finally, c is the constant value over here, and again, the negative has to go with the number to its right. So we have a equals 1, b equals negative 2, and c equals negative 1. So by the quadratic formula, the solutions to this equation are x equals, and now we're going to use the quadratic formula up here. So I'm going to duplicate the quadratic formula above, negative b plus or minus the square root of b squared minus 4ac all over 2a, and we'll go ahead and write in what that actually is in this case. So negative b, that's going to be negative, our value of b in our problem is negative 2, plus or minus the square root of, and now we're plugging in b, a, and c where they go. So b squared is negative 2 squared minus 4 times a, which is 1, times c, which is negative 1, and this is all over 2 times a, and a is, again, 1. So that's what the solutions are. Now, of course, we're going to want to simplify this. That's absolutely essential. So let's go ahead and do this. So I'll rewrite things down here, and I'll simplify things as I go. So the first term on the top is negative 2. That simplifies to just being 2. Then we have plus or minus the square root of negative 2 squared is 4. Negative 2 times negative 2 is 4. And then we've got these three numbers over here. We've got negative 4 times 1 times negative 1. The product of all those is positive 4. And so we get plus 4 when we simplify the rest of that expression inside the radical. And then the denominator is 2. Simplifying things further, that means that we get 2 plus the square root of 8 over 2. You do want to simplify your radicals when you get to this point and write 2 plus or minus the square root of 4 times the square root of 2 over 2. So we do that because 4 is a perfect square, which is a factor of 8. And so we get 2 plus or minus 2 times the square root of 2 over 2. Now we can see here that we actually have a common factor of 2 in the numerator and denominator. We can factor a 2 out of the numerator and get 1 plus or minus the square root of 2 left behind, and then 2 in the denominator. And that allows us to cancel our 2's because they are now both factors in their respective parts of the fraction. So that means that x is equal to 1 plus or minus the square root of 2 is our solution. Another way of writing this would be to say that the solution set is the set containing 1 plus the square root of 2 and 1 minus the square root of 2. So applying the quadratic formula allows us to find the solutions to this equation even though we couldn't factor it. It gives us another way of getting there. Now, before we go on to some more examples, let's check that these numbers are in fact solutions to this equation so that we can have some confidence that the quadratic formula is actually giving us what we want, actually giving us solutions to the equation. So we're looking at the equation x squared minus 2x minus 1 equals 0, and the claim that the quadratic formula gives us is that 1 plus square root of 2 and 1 minus square root of 2 are solutions. So let's check. Let's check the number 1 plus square root of 2. We'll plug that into the equation and get 1 plus square root of 2 squared minus 2 times 1 plus square root of 2 minus 1. And let's simplify that down, see what we get. Now 1 plus square root of 2 squared is going to have to FOIL out. We're going to have to multiply it by itself. So if we take 1 plus the square root of 2 times 1 plus the square root of 2, that's what 1 plus square root of 2 squared is going to be. Now we can distribute the negative 2 through in the middle and get negative 2 minus 2 times the square root of 2, and then minus 1 on the outside. Distributing the two radical terms here, we get 1 times 1 is 1, 1 times square root of 2 is square root of 2. Square root of 2 times 1 is the square root of 2. And the square root of 2 times the square root of 2 is the square root of 4, which of course we're going to simplify to just being 2. So we get 1 plus 2 times the square root of 2 plus 2 minus 2 minus 2 square root of 2 minus 1, and we see that everything cancels out. We see that the 1 here cancels with the negative 1 over here. The 2 square root of 2 cancels with a minus 2 square root of 2. And the positive 2 cancels with the negative 2. And so we do, in fact, get 0 out of it. And so that checks out that 1 plus the square root of 2 is a solution to this equation. And a similar check for 1 minus square root of 2 will also show that when you plug it into the left-hand side of our original equation, we do in fact get 0 out of it. So this at least gives an example for convincing yourself that the quadratic formula is in fact giving you what you need. Let's do another example. We want to solve x squared plus 4x plus 8 equals 0, and we want to find the solutions. Let me reproduce the quadratic formula. Here, so we can remember it. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And once again, if you look at this equation, you'll find that you actually can't factor it. That there are no numbers that add to equal 8 and, multiply to equal 8 and add to equal 4. And so we will want to use the quadratic formula. Now, once again, it's not a bad idea to be very explicit about what a, b, and c are. So in this case, a will be 1 again, because there's no number written in front of the x. B will be 4, and c will be 8. So we can plug these numbers into the formula to find the solutions. We get x is equal to negative b, which is 4, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 8, all over 2 times a, which is 1. Simplifying this, we get negative 4 on the top, plus or minus the square root of 16. Now 4 times 1 times 8 is 32. So we get 4 plus or minus the square root of 16 minus 32 over 2. So that gives us negative 4 plus or minus the square root of negative 16 over 2. And here's where we need to use our knowledge of complex numbers to continue the process and to write things down. Because the square root of negative 16 is not a real number. So the only way we have of expressing this is using our imaginary unit I. So this is going to be negative 4 plus or minus the square root of negative 1 times the square root of 16 over 2. And so when we write that using I, this gives us negative 4 plus or minus I times the square root of 16, which is 4, all over 2. Now, once again, you'll notice that everything in the top is divisible by 2, and everything in the bottom of this fraction is divisible by 2. And so we can factor a 2 out and cancel. Alternatively, we can take a small shortcut here and we can just cancel 2 from everything now, but it's important that when we do that, we cancel 2 from each term in the numerator and the denominator. We can't cancel this 2 with just the first -4. We also can't cancel the 2 with just the 4 on the right. If we're going to cancel the 2, we're going to cancel it with everything, with each term in the numerator. Now, if you're unsure about that, then go ahead and simplify it the way that we did the previous problem, where you just factor a 2 out of both terms in the numerator and then cancel. And that works just fine. So we find that our solutions are x is equal to -2 plus 2i, or x is equal to -2 minus 2i. So the solution set of this equation is -2 plus 2i and -2 minus 2i. So one thing that you'll notice here, well, obviously, is that our answers are now no longer real numbers. They're complex numbers. They have non-zero imaginary part. Whereas the previous example involved 2 solutions that were both real numbers. Even though they both had square roots in them, they were still real numbers. So we can see here that there are different types of solution sets that quadratic equations can have. You can have 2 real numbers, as we saw in the first example. We could have 2 complex solutions, as we have in the current example. And we can actually have one more different kind. Let's look at the following equation. Let's look at solving 2x squared minus 12x plus 18 equals 0. Now, this one actually can be factored. But let's imagine that we don't want to do that for a second, because we're going to be using something about the quadratic formula to give us some insight into what's going on. Let's use the quadratic formula again. Where x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. Here are our solutions. So our solutions here are x equals, now this time I won't explicitly write down what a, b, and c are. I'll just go ahead and put them into the formula as I read it out. So x is equal to -b. Now b is the coefficient of x, so that's -12, plus or minus the square root of b squared, so that's -12 squared, minus 4 times a, which is 2, times c, which is 18, all over 2 times a, which is 2. So we'll simplify this down and get 12 plus or minus the square root of, now -12 squared is -12 times -12, that's 144, minus, and now 4 times 2 is 8, and 8 times 18 works out to be also 144, and then the denominator is 4. So then we get 12 plus or minus the square root of 144 minus 144 is 0. And if we add or subtract 0 from 12, we get the same thing out of it, no matter what. So because the square root of 0 is 0, we can actually just not write that at all. That's just 12 plus or minus 0. So that's just 12. So we get 12 over 4, which is in fact 3. So in this case, we have only one solution, which is x equals 3. So our solution set is just the single number 3. So those were 3 examples showing how we use the quadratic formula to find the solution sets to quadratic equations. And they give the 3 different types of solutions that we can get out of a quadratic equation. And we can take advantage of this. We can analyze some of what's going on here. So let's think about why we got these different kinds of solutions in each case. Well, if we go back to the first example, we can see that we got 2 different real numbers out of this, basically because the square root part, the thing that's being added or subtracted, wound up being a positive number, wound up being the square root of 2, or the square root of 8 rather, which we reduced eventually. So we, at this point, got 2 plus or minus the square root of 8 over 2, and that gave us 2 different real number answers. On the next problem, the stuff inside the square root wound up being negative 16. And so we still got 2 different answers because we're adding and subtracting this square root of negative 16. But now, because we're taking the square root of a negative number, we got complex solutions out of it, non-real solutions out of the quadratic formula. And finally, in our third example, the things inside the square root wound up being 0. And now, even though we've got a plus or minus in the formula here, adding or subtracting 0 doesn't actually change anything. And so we only got a single number out of the quadratic formula. So we can use that part of the quadratic formula, x equals negative b plus or minus the square root b squared minus 4ac over 2a, to predict, describe, know how many and what kind of solutions we're going to have. And it's all based on the stuff that's inside the square root. Now, this is important enough that it actually has a name. We call it the discriminant. The discriminant of the equation ax squared plus bx plus c equals 0 is the number b squared minus 4ac, and that's it. So in particular, notice it doesn't include the square root. The discriminant of ax squared plus bx plus c equals 0 is the number b squared minus 4ac. It's the stuff that goes inside the square root. Now we have the following fact. If b squared minus 4ac is greater than 0, then the equation has 2 real solutions. This is what we saw in our first example. If the discriminant is positive, then that means that the square root part of the formula is going to be a positive number. And so we get negative b plus or minus some positive number divided by 2a. We're going to get 2 different real numbers out of it. On the other hand, if b squared minus 4ac is less than 0, the equation has 2 complex, in particular non-real, solutions. That's what we saw in the second problem, where the discriminant was negative And so in the formula, we wind up adding and subtracting the square root of a negative number, which gives us two different things, but it gives us two different complex things. And finally, if b squared minus 4ac is equal to 0, the equation has one real solution. This was our last example. If the discriminant winds up being 0, then our equation, our formula rather, just becomes negative b plus or minus 0 over 2a. Adding or subtracting 0 doesn't change anything, and so our solution will just be negative b over 2a. So we can use the discriminant to look at an equation and know ahead of time whether it's going to have two real solutions, two complex solutions, or one real solution. In particular, also, this means that these are the only possible types of solution sets for a quadratic equation, because the discriminant will always be either positive, negative, or 0. So let's look at an example of using this. We could ask, what kind of solutions does the equation x squared plus 3x plus 5 equals 0 have? And by what kind we mean here, do we have two real solutions, two complex solutions, or one real solution? So to answer this, we look at the discriminant. The discriminant is b squared minus 4ac. In our case, that's going to be 3 squared minus 4 times a, which was 1, times c, which is 5, which gives us 9 minus 20, because 4 times 1 times 5 is 20, which is negative 11. Now, the actual value of the discriminant we don't care about for answering this problem. We just care about whether it's positive, negative, or 0. And negative 11 is negative. It's less than 0. So that tells us that x squared plus 3x plus 5 equals 0 has two complex solutions. So we can use the discriminant to look at any quadratic equation and figure out whether it has two real solutions, two complex solutions, or one real solution. And this is sometimes relevant to us in real life problems. Sometimes you're going to be dealing with problems where complex solutions don't make any sense. And so you can use the discriminant to look at an equation related to your problem and know whether there are any real solutions at all, because often those are the only kind that you care about. And that can sometimes allow you to give an answer to a problem and say that there are no solutions to this without actually having to go through the process of computing the solutions using the quadratic formula. Just one part of it, just this discriminant which determines what kind of solutions there are to the equation. All right, so for the last part of this talk, I want to do a proof of the quadratic formula. This is sometimes helpful to see, to understand why the quadratic formula works. Did it just, appear out of nowhere? Well, of course it didn't. There's actually good reason for why the quadratic formula works. Some people do find it helpful to see how it came about. That can be helpful for memorizing it. So we're going to use a technique called completing the square. And what this uses is the following fact. If I have x squared plus, let me use a letter that we haven't used yet so far. If I have x squared plus fx, and then if I happen to have f over 2 squared, well, this expression right here, where f is some real number, is equal to x plus f over 2 squared. If f is a real number, then this means that the left-hand expression is what we call a perfect square trinomial. It's the square of some expression, and we can see that over here on the right. Now, to check this, the easiest way to check this is just by expanding out the right-hand side. X plus f over 2 squared will be x plus f over 2 times x plus f over 2, which will give us, when we multiply everything out, x squared plus x times f over 2 would be f over 2 times x. F over 2 times x is f over 2 times x. And then f over 2 times f over 2 is f over 2 squared, which simplifies down to just being x squared plus, and then f over 2 plus f over 2 would be 2f over 2, which is just f. So we get x squared plus fx plus f over 2 squared. So this fact is what we're going to use. If we ever have x squared plus some number times x plus half of that number squared, we can use this equation right here. And that's part of what we're going to use as we go and prove that the quadratic formula gives us what we want. So let me give myself some more space here. I want to write down in the corner here the result that I just mentioned, the completing the square result. That if I have x squared plus fx plus f over 2 squared, that equals x plus f over 2 squared. I'm going to keep that in a box over here for when we need it. So let's suppose that we have the following equation: ax squared plus bx plus c equals 0. And we want to try and solve this for x. Well, I'm going to go about this a slightly different way than we normally do. I'm going to imagine that I can't factor this. I'm also going to imagine that that I don't have the quadratic formula yet, and I need to somehow figure out what x is, and we'll be deriving the quadratic formula in the process. So the first thing I'm going to do actually is get the x squared to have a coefficient of 1. So we're going to divide both sides of this equation by a. And we're allowed to do that by our standard algebraic techniques. So this equation is equivalent to what I get when I write ax squared over a plus bx over a plus c over a equals 0. So here I've just split up the fraction on the left across the numerators, and now these a's cancel out, and I am just left with x squared plus b over ax plus c over a equals 0. Now I'm going to subtract c over a from both sides and get x squared plus b over ax equals negative c over a. Now here's where I'm going to use my completing the square fact. I know that if I have x squared plus some number times x plus that number over 2 squared, that's a perfect square trinomial. I'm just using the blue formula in the at the top of the screen. Now, of course, I don't have that right now, but I can get that. I'm going to add something very special to both sides of my equation. I'm going to add b over 2a squared. And I'm going to add b over 2a because that's exactly what I need on the left-hand side to turn it into a perfect square trinomial. It's half of the coefficient of x squared. And I'm going to do the same thing on the right-hand side to balance it out. So that means that my equation is equivalent to the following: x squared plus b over ax plus b over 2a squared, which is half of b over a, then squared, equals, and then on the right-hand side here, I'm going to write this as b squared over 4a squared minus c over a. I'm going to go ahead and apply that power to everything inside the fraction. Now we can do a couple of things. First of all, I'm going to use my completing the square fact. So I'm going to use the blue fact up at the top, where f is equal to b over a. Instead of f, I have b over a, and I'm going to write this as x plus b over 2a squared. So that's what the fact in the upper right gave us. I'm also going to combine the two fractions on the right together by multiplying the c over a fraction by 4a over 4a to give it a denominator of 4a squared. So the right-hand side will become b squared minus 4ac all over 4a squared. And now we are getting close. So what we have now is that x plus b over 2a squared is equal to the expression on the right. Well, if some expression squared equals the expression on the right, we know what that means. This means that x plus b over 2a equals the square root of that thing, or the negative of the square root of that thing. This means that we can look at b squared minus 4ac all over 4a squared, and continue to simplify from there. So this is going to be plus or minus. Now I'm going to apply the square root to the top and bottom of the fraction on the right. So on the top, we just get the square root of b squared minus 4ac. Nothing we can do there, but we can take the square root of 4a squared. And the square root of 4a squared is exactly 2a. Now finally, we can get x by itself by subtracting b over 2a from both sides to get x is equal to negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a, and therefore x is equal to, by combining them together with the same denominator, negative b plus or minus b squared minus 4ac all over 2a. Thus, we have the quadratic formula as we saw before, and so we have proven it. So the quadratic formula is very useful for lots of problems that we want to work with. We are very blessed to have it, and we'll continue to use it very often throughout the rest of the course.